For over half a century, the Boeing 737 has been an undisputed workhorse of the skies. Since its first flight in 1967, this venerable narrow-body jet has become one of the most successful aircraft in history, connecting cities and cultures across the globe. With over 10,000 units delivered, its enduring legacy is a testament to its robust design, reliability, and constant evolution, consistently adapting to the changing demands of air travel and remaining a global favorite. But even a legend must evolve. As the 21st century dawned, fierce competition emerged, notably from rival Airbus and its A320neo, which promised significant fuel savings and reduced emissions. Airlines demanded more efficient aircraft to cut operational costs and meet environmental regulations. Boeing faced the critical challenge of modernizing its most popular aircraft while retaining its core strengths and operational commonality for airline fleets. The answer was clear: an upgraded version of the beloved 737. This new iteration was christened the Boeing 737 MAX. It was designed to be Boeing's most advanced and fuel-efficient single-aisle aircraft yet, boasting impressive improvements in range and operational costs. The most visible and significant change lay in its engines: larger, more powerful, and significantly more fuel-efficient LEAP 1B turbofans. These cutting-edge engines were the cornerstone of the MAX promise, offering airlines an immediate competitive edge in a demanding market focused on efficiency. However, integrating these larger engines into the existing 737 airframe presented a unique engineering challenge. The original 737 was designed with a very low ground clearance. The distance between the engine and the runway was minimal. To accommodate the new, wider LEAP 1B engines, engineers couldn't simply hang them lower without risking ground strikes. The solution was to mount the engine slightly forward and higher on the wing, a subtle change that significantly altered the aircraft's aerodynamics. This subtle forward and upward shift of the engines created a new aerodynamic characteristic. At certain high angles of attack, when the aircraft's nose is pitched up significantly, like during a steep climb, this new engine placement could cause the aircraft's nose to pitch further upwards, increasing stall risk. To counteract this, Boeing introduced the Maneuvering Characteristics Augmentation System, or MCAS. This software-based system was designed to automatically push the nose down, maintaining familiar handling characteristics. Originally, MCAS was intended to operate in specific, high-stress flight conditions, primarily when the aircraft approached a stall. Its function was to gently, almost imperceptibly, nudge the aircraft's nose down to prevent an uncontrolled stall. The system relied on data from a single angle of attack, or AOA, sensor on the exterior fuselage. If this sensor detected a high angle, MCAS would activate, commanding the horizontal stabilizer, the small wing at the tail, to push the nose down. The crucial difference between the 737 MAX and its predecessors, like the 737 Next Generation, or NG, lay in MCAS's presence and authority. Older 737s lacked such a system, as their aerodynamics were inherently stable. On the MAX, MCAS had significant power to trim the aircraft. Critically, the initial MCAS design allowed it to repeatedly activate based on input from just one AOA sensor, even if that sensor was providing incorrect or erroneous data, potentially overriding pilot input. Another key aspect differentiating the 737 MAX's introduction was the pilot information provided. Boeing intended MCAS to be a background system, rarely activating, so its full operational details were not extensively highlighted in initial training or manuals. Pilots, many transitioning from earlier 737 models, were trained assuming very similar handling. The complex, automated nature of MCAS, coupled with its potential for repeated activation from a single sensor, was largely unknown to flight crews. Tragically, this combination of design choices and limited pilot awareness led to catastrophic outcomes. In late 2018 and early 2019, two 737 MAX aircraft crashed, claiming hundreds of lives. Investigations revealed that in both instances, a single, faulty angle of attack sensor provided incorrect data to MCAS. Believing the aircraft was pitching up excessively, MCAS repeatedly commanded the nose down, despite pilots' efforts to counteract it. This unexpected and powerful automatic input proved overwhelming. The accidents triggered an unprecedented global response. Aviation authorities worldwide, including the Federal Aviation Administration, FAA, swiftly grounded the entire 737 MAX fleet. This rare and drastic measure underscored the situation's severity. Extensive investigations ensued, scrutinizing every aspect of the aircraft's design, certification, and software. The grounding allowed engineers and regulators crucial time to understand the failures, analyze the system, and formulate comprehensive solutions for its safe return to service. The core of the redesign focused on enhancing MCAS's safety and redundancy. Key changes included requiring input from both angle of attack sensors, rather than just one, to activate MCAS. If these two sensors disagreed significantly, MCAS would not engage. Furthermore, MCAS's authority was now limited, ensuring pilots could always counteract its commands using their control columns. Boeing also implemented mandatory new pilot training and revised flight manuals, addressing every identified safety gap. After nearly 2 years of intensive review, software updates, and rigorous recertification processes by aviation authorities globally, the Boeing 737 MAX was cleared to return to service. Its journey highlights the critical importance of continuous safety scrutiny and the evolution of aerospace engineering. The differences that made the MAX unique also presented unprecedented challenges. Today, the 737 MAX embodies enhanced safety measures and a renewed commitment to pilot awareness and robust system design, flying once again